Learn like a pro.
If you want to know how much a bag of flour or a metal sphere weighs, it's pretty straightforward. You drop it on a scale, read the number in grams or pounds, and you're done. But if you try to place a single atom on that exact same digital laboratory balance, nothing happens. The scale reads 0.000 grams. Atoms are so incredibly small that on a macroscopic scale, they possess practically zero mass. To build precise chemical reactions, chemists need to know exactly how much of each ingredient they are combining. You can't follow a recipe if your measuring tools can't detect your ingredients. Because absolute units like grams are entirely useless for measuring individual atoms, scientists had to throw out the standard scale altogether. They needed a new conceptual framework to weigh the invisible. Instead of trying to weigh atoms in absolute grams, chemists established a universal comparison standard. They decided to weigh every element in the universe relative to one specific atom, carbon-12. This image shows a conceptual model of carbon-12 divided into 12 equal slices. By taking exactly 1/12 of this atom and pulling it away, scientists created the fundamental unit of chemical mass. Every other element is weighed relative to this specific slice. We call this relative atomic mass, or AR for short. This graphic shows a balancing scale comparing the mass of a single atom to those 12 carbon slices. The formula is exactly that: the average mass of one atom of an element divided by 1/12 the mass of a carbon-12 atom. Because AR is just a ratio comparing one mass to another, it is a pure number. It has absolutely no units attached to it. There are no grams and no ounces, just a universal mathematical blueprint that lets us compare the weight of any two atoms. That system works in theory, but the real world reveals a curveball. Elements aren't perfectly uniform. Most elements exist as isotopes, versions with slightly different masses. This diagram shows potassium sorting into bins. In nature, it comes in three versions: K39, K40, and K41. They appear in vastly different percentage abundances, with K39 making up over 93%. To get a usable baseline number, chemists calculate a weighted average based on isotope abundance. This image visualizes that math as a physical fulcrum balancing the three potassium isotope clusters, pinpointing the exact 39.1 average based on their abundance. The relative atomic mass number on the periodic table is actually this precise weighted average. It accounts for all natural variations rather than assuming every atom is identical. Scaling up to complex molecules, this mass taxonomy matrix outlines the progression from single elements to covalent and ionic structures. Whether called relative molecular mass or relative formula mass, both MR, the universal rule confirms they share the exact same unitless calculation logic. Finding the total mass of a compound is a simple assembly process. To calculate the MR, you just snap the individual atomic values, or AR, together. For a simple binary compound like magnesium oxide, MgO, this calculation blueprint shows a magnesium atom with an AR of 24 and oxygen at 16. We multiply 1 times 24 and 1 times 16, adding them to equal a total MR of 40. The same rule applies to complex molecules like nitric acid, HNO3. This exploded view shows one hydrogen atom at an AR of 1, one nitrogen at 14, and 3 oxygen atoms at 16 each. Adding these values gives a total MR of 63. By treating invisible elements as standardized, unitless building blocks, we can quickly map out the mass of any molecular structure using simple addition. Once we know how to build molecules up, analytical chemistry requires us to reverse the process. We tear compounds down to find the specific proportions of their ingredients. This diagram isolates a single element block within a larger compound to visualize its percentage mass. To calculate the exact percentage mass of calcium in calcium fluoride, we use a 3-step calculation. Step 1. Identify calcium's AR, 40. Step 2. Calculate the total MR, 78. Step 3. Apply the formula. 40 divided by 78 times 100% yields 51.3%. This percentage mass formula bridges the gap between theoretical math and the physical lab. It tells chemists the exact physical proportions of ingredients needed for real-world synthesis. Because weighing a single atom is physically impossible, chemists created a universal baseline using carbon-12. From there, we scale up individual atomic values to predict the mass of complex molecules, and then deconstruct those structures to identify the exact proportions of their ingredients. This relative system is a mathematical blueprint that successfully turns the impossible task of weighing the invisible into a simple, scalable reality.